Guys, thank you for enjoying real convenience from this channel, Telecom Academy. We are affording you the opportunity to study from anywhere, at any time and place, and from any device. And this is how we define real convenience. Electrical engineering technology, and this time, Thevenin theorem. Let us enjoy. And if you are new to this channel, don't forget to like, share, comment, and above all, to subscribe. As usual, Motion Marfu is my name, and motionmarfu60@gmail.com. You can also find me on WhatsApp +26371753586. This time I am bringing you DC Thevenin theorem, and I hope you are going to enjoy it. Let us proceed right into our theory. First, a look at our objectives, and by the end of this video presentation, you guys should be able to, number one, state Thevenin's theorem, and you must also be able to apply it to simplify circuit analysis. Then you must also be able to describe a form of a Thevenin equivalent circuit voltage source and its resistance. Then you must be able to obtain the Thevenin equivalent voltage source as well as Thevenin resistance. Then you must also be able to explain terminal equivalence in the context of Thevenin theorem. Then last but not least, guys, you should be able to Thevenize a portion of a given circuit. Let us proceed. One of the major functions or applications of Thevenin theorem is the reduction in complexity of networks. That is, it simplifies analysis and design, and it can be used in the following applications. Number one, to analyze network resources that are not in series or in parallel, just like superposition. And number two, it can be used to reduce the number of components required to establish the same characteristics at the output terminals. In other words, we'll find an equivalent circuit with fewer components when compared to the complex network. Then the third application is it can be used to invest the effect of changing a particular component on the behavior of a network without having to analyze the entire network after each change. So it can be used for that investigative purpose. We start by stating the theorem, and it says any two-terminal DC network can be replaced by an equivalent circuit consisting solely of a voltage source and a series resistor. That's a simplified form of Thevenin theorem. Can you take note of the following? We need an equivalent voltage source, and we call this V Thevenin or E Thevenin, and this is our equivalent voltage source. And the equivalent circuit is also made up of a series resistor, and that series resistor is called R Thevenin. And we talk of any two-terminal DC network. So Thevenin's theorem is also applied to AC network. But in this video, we are looking at a DC network. So we talk of E Thevenin. And what is E Thevenin? This is the open circuit or no load voltage between the two terminals, and these are our two terminals A and B, and we know that the voltage between this open circuit is E Thevenin. It is also known as V Thevenin. Please, then R Thevenin is this series resistor, and it is the total resistance that appears between the two terminals in a given circuit when all sources are replaced by their internal resistance. You remember internal resistance when we did superposition theorem. So as I said, E Thevenin, we know E stands for EMF. E Thevenin is also known as V Thevenin, with E standing for EMF and V standing for voltage, and the two are used interchangeably. Guys, take note of our Thevenin equivalent circuit. If you don't know the steps, then you cannot simplify circuits using Thevenin theorem. So we are not going to look at these steps. And step number one is you are going to remove the portion of the network where the Thevenin equivalent circuit is found. And after removing that portion of the network, we are going to mark the remaining terminals of the two-terminal network. Then how do we find R Thevenin? R Thevenin is the next step, and you first set all sources to 0. And how do you do that? You replace the voltage source by a short circuit and the current source by an open circuit, and then we find the resultant resistance from the two terminals that have been marked. Then the fourth step is we must find Thevenin. And how do we find Thevenin? We do that by first returning all voltage and current sources to their original position, and we find the open circuit voltage between the two marked terminals. And we do that by finding the effect of voltage or current source. Don't worry, it will be easy when we do some examples. Equivalent circuit with the portion of the circuit previously removed being replaced between the marked terminals, and this ABC shows the steps summarized. So we are going to mark the two terminals A and B, and this is our Thevenin. This is our Thevenin, which is the open circuit voltage. And how do we find Thevenin? Guys, we use the voltage divider rule. This you must be now conversant with. And how do we find the voltage divider? The voltage between A and B is the same as the voltage between R2. Why? Because this is as good as out of the circuit. It has no effect on current flowing through the circuit. Only R1 and R2 have got an effect. So how do we find Thevenin, which is equal to R2? We simply say R2 multiplied by the supply voltage Vs divided by the sum of the resistance R1 plus R2. So this is how you find Thevenin or Thevenin. The two terms are used interchangeably. We now want to find Thevenin. Right, we are now going to replace Vs with a short circuit. This is the short circuit, and we find the resistance from the open terminals. How do we do that? Looking from our right, we see that R1 and R2 are in parallel because they've got 2 points in common, which is this point and this point. That's where the two resistors are connected. So we find the parallel combination. That's R1 times R2 divided by R1 plus R2, and that resistance you add to R3 since it will be a series combination. Hence, we are now going to, this is the last step. We draw the equivalent circuit with Thevenin and Thevenin and the marked terminals. This is where you put to the right of these points. You now going to, that portion of the network you would have removed, you are going to replace it and answer any questions that would have been asked. So this is Thevenin theorem steps summarized. We now want to solve complex circuits using Thevenin theorem, and we have got question 1, and it says find Thevenin equivalent circuit between A and B. This is our A and B, so this is the portion that we are going to remove, and this diagram shows test 1 and 2 covered. Remove RL and find Thevenin. So we have removed RL, we now want to find Thevenin. Thevenin or Thevenin is the voltage across the two resistors, so we are going to add them and use voltage divider rule. So we simply say if we add the two we get 690. So we say 690 times the supply voltage divided by the sum of the three resistors, which gives us 1690. I've converted 1K to ohms. And guys, I want you to punch your calculator. You must get this value. If this is not correct, highlight that in comments section. So we have covered steps 1 and 2. We now want to go into step 3. Replace voltage source by a short circuit and find Thevenin. We've got one voltage source, so we are going to replace this with a short circuit, and we've done that in C. And guys, take note that we are finding resistance looking from Thevenin. Sorry, yes, from Thevenin. And if you are looking from Thevenin position, this resistor is in parallel with the series combination of R2 and R3. So we are now going to find the total combination of the parallel circuit. And how do we do that? We simply say 1000 divided times 690 divided by 1000 plus 690, and we add that to 1K, we get 1.41. Guys, make use of your calculators and see if this is correct. Then after that, we are going to draw the Thevenin equivalent circuit, and let's straight away proceed to the next slide. The Thevenin equivalent circuit is shown in the slide, and please take note we haven't replaced the removed part. Why? Because we don't have such questions. Is simply asking us to find the Thevenin equivalent circuit, and this is the Thevenin equivalent circuit. We now put the series resistor 1.41K, and this is our Thevenin. Then our Thevenin voltage 4.08 is this, and please take note that one to see Thevenin, word Thevenin, and also the word Thevenin, and our mark terminals, and you are done. Question number 2 reads, find the Thevenin equivalent circuit for the network in the shaded area of the network. This is our A, B, C, then D. Please take note. So we want to find the Thevenin equivalent circuit of this shaded area. And how do we do that? And we are saying circuit after removing and marking the terminals is shown. We have removed the 7 ohm resistor because we are finding the equivalent of this one. Then after that, we now want to find Thevenin. This 12 amps is going to flow solely through R1 and no current flow through R2 because there's an open circuit between A and B. So the voltage across A and B is the same as the voltage across 4 ohm. So how do we find that? It's 12 times 4 and your Thevenin is 48 volts. We now want to find R Thevenin. How do we find R Thevenin? This is a current source. So we are going to replace it with an open circuit. And this is the equivalent circuit we are going to use to find R Thevenin. And looking from this direction, the total resistance, which is R Thevenin, is equal to 2 plus 4. And this is going to give us 6 ohm. We are now going to draw the equivalent circuit and replace the removed part, which is the circuit to the right of A and B. So this is our Thevenin equivalent. Please take note, E Thevenin 48 volts, R Thevenin 6 ohm, and we have replaced the resistor we had removed, the 7 ohm, and you are done. So simple. As long as you mastered your resistors in series, in parallel, and your voltage divider rule, the current divider rule, the effect of removing a short circuit, then you are done. Problem number 3, at this time we've got 3 sources. Must be able to simplify or to find rather Thevenin equivalent circuit of complex network. Or a circuit with 3 sources is a bit complex, but you'll be able to do that. Let us go through this example. We'll start with the first part. Find the Thevenin equivalent circuit for the portion of the network in the shaded area. So we want to find the equivalent circuit, which when we replace this circuit, the current through 8 ohm will remain the same. So how do we proceed? We are going to mark the terminals and remove the marked terminals, and this we have done. We've done that. So we are going to remove the 2 and 8 ohm resistor. And let's find E Thevenin. How do we find E Thevenin? E Thevenin, we are going to replace the 18 volt source E1 with a short circuit, and the current source 2 amps with an open circuit, and we'll be looking from this side. And how do we find the total resistance? These 2 resistors are in series, and this combination is in parallel with 4 ohm resistor. So we are going to say 4 ohm parallel 4 plus 6, and you must find 5.5 ohms. How are we going to find E Thevenin? E Thevenin means that to consider the effect of each source independently, then we find the algebraic sum. Let's proceed to the next slide to see how we should do so. We are now going to consider the effect of the voltage source and a current source individually, and we are starting with the voltage source. So we now want to find E prime Thevenin. Why prime? Because this is not the actual E Thevenin or V Thevenin. So we now want to find the voltage across 12 ohm, and we have replaced this with an open circuit. So these 1, 2, 3 are in series. So to find E Thevenin, which is the voltage between this point and this point, we use voltage divider rule. 12 times the input voltage, 18 divided by the sum of the 3, which is 22. And guys, punch your calculator, you must get 9.82 volts. We now want to consider the effect of the current source, which means that we are going to replace the E1 voltage source with a short circuit, and we have done, this is the short circuit. And the E prime Thevenin is the voltage across 12 ohm resistor, or is, yes, with the voltage source replaced by a short circuit. So this current is proceeding in this direction. So some is going to branch, some going through the 4 ohm resistor and some going through the 6 ohm resistor. So we now want to find our E Thevenin, and this is our E Thevenin. So this is current divider rule in action. I want to find if we add the 2 resistors, they are in series because our current is going to flow in this direction, in this direction, in this direction. Yes. like that. So considering the effect of the current source, the simplified circuit is as shown. This is the simplified circuit. Sometimes they need to simplify the circuit so that you can visualize. The current through the 12 ohm is our Thevenin prime, and the current through it, we are going to use CDR. So we are going to say 4 times the input current 2 amps divided by the sum of the parallel combination. That's 22, and we are going to get 0.364 amps. This is the current flowing through this resistor. How do we find E Thevenin? E Thevenin is, this is a negative voltage. Please take note, this is a negative voltage. We've got a drop, we've got a plus there and a negative there, so we are going to regard it as a negative voltage. So hence the minus sign. So we are going to say I times R. This is minus 4.3 volts. So we are now going to consider the summation. You know, guys, if you remember, if you move from a positive to negative of the across a resistor or a voltage source, from positive to negative, that's a minus. From negative to positive, that is a positive voltage. From positive to negative, that is a negative voltage. Hence the use of this minus sign or this negative voltage. If we add the two, we are finding the algebraic sum, and it's going to be 9.82 volts, which is this volts, or the E Thevenin due to E1, and plus this, which is E Thevenin due to the current source, and if you add the two, you get 5.5 volts. The last slide on Thevenin theorem, and the last part of the work, problem number 3. We are now going to reconstruct the network with the Thevenin equivalent circuit in place, and we are now going to find VA. So we have replaced the removed part, which is E2 and this resistor, and this shaded area shows the Thevenin equivalent circuit. Please take note, the ground is the same as the negative terminal. So how do we find VA? VA is the voltage between this point and this point, which is the voltage across the 8 ohm resistor. And please take note, let's analyze the series combination of these two resistors. We are going to add the two. Take note, the negative is connected to the positive, hence the two are connected in series. So it's 16 volts, which is E2 plus E7, which is 5.5. Then you multiply that by 8 ohms and you divide by the sum of the two resistors, and you must get 12.76 volts. Guys, you are done, and we are also done insofar as Thevenin's theorem is concerned. The key points: first, know that you must mark the two terminals, then you remove the part, and after removing the part, we find R Thevenin and V Thevenin. How do you find R Thevenin? By setting to 0 all voltage sources and current sources, then you find the Thevenin equivalent resistance. And V Thevenin is the open circuit voltage, and if there are, and how do you find the equivalent V Thevenin? You consider the effect of each source alone, and you are done. From there, the way how you proceed is determined by follow-up questions. Guys, I hope you have achieved all the objectives. You are able to find R Thevenin, you are able to find V Thevenin, and you are also able to produce the Thevenin equivalent circuit.